This paper addresses the challenging problem of predicting phase behavior in charged polymer blends, a topic important for designing advanced polymer materials with desired properties. Understanding how different charged polymers blend and phase separate is critical because it informs material design for applications ranging from coatings to membranes. Traditional simulation techniques, such as the random phase approximation (RPA), are computationally expensive and time-consuming, hindering rapid exploration of large parameter spaces. The authors propose a whitebox surrogate modeling approach that combines physical insight with machine learning to accelerate phase prediction without sacrificing accuracy. This approach uses a structured workflow that connects system parameters to phase behavior predictions through a surrogate model informed by RPA simulations. Through this method, they aim to achieve significant speedups in phase diagram construction and enable uncertainty quantification. The following figures will detail the workflow, accuracy, computational efficiency, and application of this surrogate model across various scenarios, demonstrating its potential as a practical tool for materials design. Figure 1 illustrates the overall workflow for the random phase approximation simulation used to predict polymer phase behavior from system parameters. This workflow is central to the whitebox method proposed. It begins with inputting polymer system parameters such as composition and interaction specifics. These parameters feed into the RPA model, which calculates key quantities like the inverse form factor matrix. From these calculations, the phase behavior of the polymer blend is determined. Importantly, this workflow not only predicts the phase, but also provides a measure of uncertainty in the predictions. This comprehensive integration of parameter inputs through the RPA simulation to phase output forms the foundation for the surrogate model development presented in this paper. Figure 2 presents the predictive performance of the surrogate model by comparing true and predicted values for two components of the form factor matrix, log PG11 and log PG112. Panels A through C correspond to log PG11, while panels D through F correspond to log PG112, each using 50 training points. Panels A and D show the true values, panels B and E show the surrogate model's predictions, and panels C and F show the residuals, or errors between predicted and true values. The figure demonstrates that the surrogate model achieves close agreement with true RPA simulation outputs, with residuals kept relatively low. Panel F in particular illustrates the error distribution for log PG112. These results highlight the surrogate model's capability to accurately replicate key input components needed for phase predictions from limited training data, enabling faster computations downstream. Figure 3 compares the phase prediction accuracy of 4 different models as a function of training dataset size. Panel A shows results for a uniformly sampled test set, while Panel B shows results for a grid-based architecture test set. Each accuracy value is averaged over predictions from models trained on 5 different training datasets, selected by a boundary-driven maximum design. Vertical bars indicate minimum and maximum accuracies across these datasets. The figure shows our whitebox surrogate method significantly outperforms competing approaches across both test sets and all training sizes. Accuracy improves with more training data, but even at small sample sizes, the whitebox model achieves high accuracy in phase prediction. This demonstrates the approach's robustness and efficiency in learning complex phase behavior from limited data while generalizing well to different test conditions. Figure 4 compares computational time between the surrogate model approach, specifically using 50 training samples, and the full RPA simulation to generate increasingly large sets of samples. Solid lines show computational time for obtaining the inverse form factor matrix G-1, while dashed lines show time for obtaining phase labels. The cost of using the surrogate prediction includes time for training the surrogate models, generating predictions, and plugging those results back into the RPA framework. The figure demonstrates that the surrogate approach significantly reduces computational cost, especially as the number of samples grows. This efficiency enables rapid phase screening that would be computationally prohibitive using direct RPA simulations alone. Thus, this figure validates the surrogate's utility in accelerating large-scale phase behavior exploration. Figure 5 presents phase diagrams in the alpha A versus alpha B plane generated by the proposed whitebox surrogate method compared to full RPA simulations. Panels A and B vary the chain length ratio R, while panels C and D vary the chemical incompatibility parameter NHIAB. Panel E compares computational times required to generate the phase diagrams for these two approaches. The results show that the surrogate closely matches full simulations in terms of predicted phase boundaries across varying physical parameters. The surrogate produces these results at a fraction of the computational time, indicating its effectiveness for fast material screening. This illustrates how the surrogate method can be used practically to design polymer blends with tailored phase behavior by varying key system parameters with high efficiency. Figure 6 shows phase boundaries separating compatibilized states, including disordered or microphase separated states, from macrophase separated states. Panel A plots the critical chemical incompatibility parameter Na-cap-Ab as a function of polymer fraction Fa for varying chain length ratios R. Panel B shows critical Na-cap-Ab versus Fa for different values of interaction parameter alpha. Unless stated otherwise, alpha is set to 0.25, and other parameters hold at baseline values. Importantly, the predicted phase boundaries from the surrogate model and the truth from full RPA simulations visually overlap almost perfectly. This validates the surrogate's accuracy in reliably capturing critical transition points crucial for materials design. The figure highlights the surrogate's potential for swift, accurate identification of phase boundaries under diverse conditions. Figure 7a compares phase prediction accuracy on a 2,000-point test set using three methods: raw surrogate predictions without corrections, shown in green, sample-corrected predictions that ensure positive definite form factor matrices in red, and predictions augmented with additional uncertainty-driven simulations indicated in blue. The dashed line marks perfect accuracy equals 1. The figure shows that correcting predictions improves accuracy, and further incorporating uncertainty-driven simulations substantially closes the accuracy gap to near-perfect prediction. Panel B quantifies the proportion of test samples flagged as requiring these uncertainty-driven simulations, demonstrating efficient adaptive refinement. The authors interpret this as evidence that incorporating uncertainty helps identify and correct challenging cases, boosting overall surrogate model reliability in phase prediction. In summary, the authors have developed a fast and accurate surrogate modeling framework for predicting phase behavior in charged polymer blends. By leveraging the physical principles embodied in the random phase approximation, combined with efficient surrogate modeling, the method achieves excellent fidelity in reproducing critical phase boundaries and form factor components from small training datasets. This whitebox approach outperforms other models in phase prediction accuracy and significantly reduces computational cost, enabling rapid generation of phase diagrams across a variety of parameter variations. Furthermore, the incorporation of uncertainty-driven corrections enhances prediction reliability and adaptivity. Together, these advances offer a practical tool for materials scientists to quickly screen polymer blends for compatibility and phase behavior. This work highlights the value of integrating physics-based simulations with data-driven techniques for accelerated materials discovery